Today we discuss periods of complex circular functions. Periods of complex circular functions. Sine z and cos z. The textbook you can see the sine z as sine x and cos x with x is complex. So we need to discuss this first. So as we know, sine z1 plus z2 can be written as sine z1 cos z2 plus cos z1 sin z2. In fact, this is a formula which we have derived in real numbers, so that is also true for complex numbers. If we replace sin z as e raised to iz minus e raised to minus iz divided by 2I, and cos z as e raised to z e raised to iz plus e raised to minus iz divided by 2. So you can prove all those formulas involving subtraction addition with real numbers using these formulas. So if we consider sine z plus 2 pi, then you can write it as sine z cos 2 pi plus cos z sine 2 pi. That is equal to, we know that sine z into cos 2 pi is 1, so this term is equal to sine z. And we know that sine 2 pi is 0, then this term will be 0, so this product is 0. So sine z plus 2 pi is equal to sine z for all z belongs to complex number C. Okay. Similarly you can get cos of z plus 2 pi is same as cos z. Okay. This shows that the periods of the circular functions cos z and sin z uh, are nothing but 2 pi. So if we write this cos z plus 4 pi equal to cos z plus 2 pi plus 2 pi, we can reduce this as cos z plus 2 pi, and hence this is equal to cos z. So we can say that not only this 2 pi is the period of cos z, but 4 pi is also a period of cos z. Clear? Similarly, you can prove that 6 pi, 8 pi are all periods of cos z and sin z as well. Another interesting fact about these circular functions uh, is when you evaluate this cos, uh, we know that cos z is nothing but e raised to iz plus e raised to minus iz all divided by 2. Okay. Put z equal to iy, a purely imaginary number. If you replace this z by iy, then what is cos iy? For y is a real number. So this will be equal to e raised to I times iy plus e to the power minus I times again iy all divided by 2. Okay. This will give e raised to minus y plus e raised to y, because I square is minus 1 divided by 2. Okay. So this is an interesting fact. Similarly, if you replace z by iy in sin z, you can get another interesting expression. We replace sin z. We know that sin z is e raised to I z minus e raised to minus I z whole divided by 2I. Okay. If you replace z by iy, you can get sin iy is equal to e raised to I times iy minus e raised to minus I times iy whole divided by 2I. Okay. So this is equal to sin iy equal to e raised to minus y minus e raised to y divided by 2y. When you take minus sign out, you can get e raised to y minus e raised to minus y whole divided by 2y. Okay, so this is equal to, if you replace this minus 1 as I square, you can cancel one I from the denominator. So you can get I times e raised to y minus e raised to minus y divided by 2. Okay, so from sin z and cos z, you can get another expression for uh, sin iy and cos iy. Okay, cos iy, we already seen that expression, that is I times e raised to y plus e raised to minus y divided by 2. Okay, so now I here, I here. So these are the two expressions. So we interested on this factor e raised to y minus e raised to minus y by 2 and e raised to y plus e raised to minus y by 2. Okay, next we will define hyperbolic functions as this is hyperbolic sine and this is hyperbolic cosine. Yeah. So next we can see the definition of hyperbolic functions. Hyperbolic functions. We define hyperbolic function as hyperbolic cosine. We can define hyperbolic cosine first. That is denoted by cos h of x. That is e raised to x plus e raised to minus x divided by 2. This is the hyperbolic cosine of x. And we can define sin h, hyperbolic sine of x. That is equal to e raised to x minus e raised to minus x divided by 2. So next we will discuss the relations between sine, hyperbolic sine and usual sine. Yeah. Uh, Before that, we can define another hyperbolic trigonometric functions. Uh, say tan hy. Tan hy is defined as sin hy divided by cos hy e raised to y minus e raised to minus y divided by e raised to y plus e raised to minus y. You can cancel the denominator too. Similarly, you can define cosec hy, that is defined as 1 by sin hy, that is equal to 2 divided by e raised to y minus e raised to minus y. So in the similar manner, you can define other trigonometric ratios, cot hy, sec hy, and so on. So from this result, we have seen that cos iy is defined as e raised to y plus e raised to minus y divided by 2. So we can write this as cos hy. Clear? So cos iy is same as cos hy, and similarly sin iy can be written as I times e raised to y minus e raised to minus y divided by 2. Therefore, this is written as I times sine of hyperbolic y. Yeah. So this is the interesting relation between cos and cos h, cos and hyperbolic cos. Similarly, this is the relation between sine and hyperbolic sine. That means if you convert cos to this hyperbolic function, you can directly replace this cos by cos hy by removing this I. In order to remove this I, we need to put I over here for sine function. Yeah, this is the important relations between cos and cos h, sine and sine. As a consequence of this, you can get tan of Iy. Okay, tan of Iy is defined as sine of Iy divided by cos of Iy. So this is equal to I times sine Hy and divided by, this is same as cos Hy. So that is equal to I times tan Hy. Okay. So we have uh, this relation between tan and hyperbolic tan. Now we can see another interesting formula. We know that for any z belongs to C, we know that cos square z plus sine square z equal to 1. Okay, you can prove this result using the expression for cos z and sine z, what we have proved in terms of e power I z. So uh, if you prove this theorem, you can write this as uh, by putting iy instead of this z, you can write this as cos square iy plus sine square iy is equal to 1, because this is true for any complex number. So you can replace that z by iy. So this can be written as cos square hy, because cos iy is same as cos hy, and plus you can write this as I square sine h square y, that is equal to 1. That is cos h square y minus sine h square y equal to 1. So this is the analogous to the formula cos square z plus sine square z equal to 1. Okay. Similarly, you can find other formulas for this hyperbolic function by replacing this cos hy as uh, cos iy and sine I times sine hy as sine iy. So in the textbook, you can see another interesting formula regarding this tan hyperbolic tan of 3x. So you can check it out from the textbook itself. That is already worked out result. Now let's see the series expression of cos hx. So we know that by definition cos hx equal to 1 by 2 times e raised to x plus e raised to minus x. We know that what is e raised to x is. So that is 1 by 2 times 1 plus x square by factorial 2 plus x cube by factorial 3 plus etc. plus 1 minus x by 1 factorial plus x square by 2 factorial minus x cube by 3 factorial etc. Then you can get this sum as half times, when you add these two, you can get 2 plus 2 times x plus 2 times, sorry, you can cancel this x here, this x with this minus x, and 2 times 2x square by factorial 2. Then you can cancel this x cube by 3 factorial and minus x cube by 3 factorial. Then you have 2 times x raised to 4 by 4 factorial plus etc. So this is nothing but 1 plus, as we cancel these two, we can write 1 plus x square by 2 factorial plus x raised to 4 by 4 factorial plus etc. Okay, so you can get the expression for cos hx. Similarly, you can find the expression for sin hx. That is sin hx equal to half e raised to half times e raised to x minus e raised to minus x. Okay. So this is equal to 1 by 2 times 1 plus x square by factorial 2 plus x cube by factorial 3 plus etc. minus of 1 minus x by 1 factorial, that is x itself, plus x square by factorial 2 minus x cube by factorial 3 plus etc. Okay. When you subtract this bracket from this, you can get half of, you can cancel this one first, then you have 2x minus, sorry, plus 2 times x cube by 3 factorial plus 2 times x raised to 5 by 5 factorial, 5 by 5 factorial plus etc. Okay, so that becomes x plus x cube by x cube divided by 3 factorial x raised to 5 divided by 5 factorial plus etc. Okay, so this is expression for sin hx. Now you can find the periods of hyperbolic functions. Periods of hyperbolic functions. Okay, for that we write cos h of x plus iy, that is equal to cos of x plus iy times I, because we know that cos iy is same as cos hy. Okay, so you can write that y by this one. So that's equal to cos of xi minus y. So that is equal to cos of minus 2 pi plus xi minus y. That is equal to cos of 2 pi I plus x plus iy times I. Okay. When you multiply this I with this bracket, you can get the first term will be minus 2 pi, that is here. Second term will be xi. Then last term will be yi square. Yi square is y into minus 1. Okay. So this is same as this one. We factor out that I from the angle, then you will get this expression. And we know that this is same as cos h of 2 pi I plus x plus iy. Now we have proved that cos h of x plus iy is same as cos h of 2 pi I plus x plus iy. So you can consider this 2 pi I as the period of hyperbolic cos. Similarly, you can prove that period of hyperbolic sine is also this 2 pi I. That is, you need to prove, I have to as an exercise, sin h of x plus iy. You can prove that this is same as sin h of 2 pi I plus x plus I. Okay, you can prove it using the you can prove this using the same method we have adopted here, or you can replace this cos h and sin h by exponential values. Then you can use the periods of exponential function to prove this. So there are some interesting problems after the section. That is, you have already discussed in the plus 2 level, separating the real and imaginary parts. The only thing is we need to use the formulas that we have discussed here to separate the real and imaginary part of some expressions. So one of the important problems for the exam point of view, are these questions. These are all worked out problems in textbook, so you need to work it out as you want, and come to me if you have any doubts or clarifications. Okay. Thank you.